Another place where crossed electric and magnetic fields appear is in the Hall effect. This is an important effect that enables us to investigate some properties of the charge carrier. So as a result, we have to at least qualitatively explain what's going on in here. First, let's describe what the effect is. We have a current carrying wire. So wire is like this in here, as shown, right? The wire is like that. We place this wire inside a perpendicular magnetic field. So the magnetic field is applied perpendicular to the wire. In that case, it appears that there is a potential difference across two sides of the wire. So in this diagram, for example, if I connect a voltmeter between these 2 points, the diagram is kind of complicated, but I'm going to simplify this diagram. So if I connect a voltmeter between these 2 points, so this voltmeter shows a reading. So either B is at a higher potential than A or has a lower potential, but there is a potential difference. So that potential difference is also called as the Hall potential. The value of that potential difference gives us some important clues about the charge carriers, right? But first of all, of course, we can, by using the sign of that Hall potential, we can determine what the sign of the charge carriers are. Now, this circular geometry is a little bit complicated. So as a result, most of the time when we are discussing the Hall effect, we are taking the wire as a rectangular in shape. So I'm going to draw it like that. So there is a rectangular wire like that, right? You can think of it as a rectangular wire slab. Of course, this is long, right? This is a long wire, but I don't draw all of it in here. So to make sure that the shape is understood correctly, I'm just showing a small portion of it. So there's a magnetic field in here, right? There's a magnetic field B, and I just choose these points in here, the point A on that side and the point B on this side. What we are saying is that this VBA potential difference, this is the Hall potential, this is the one which is non-zero, and it depends on the existence of the magnetic field. Okay, we can first start with the why there should also be a current in here. There's also a current in here, so there's a current flowing. So therefore, the Hall potential difference, of course, depends on the current as well, not only on the magnetic field, but the current as well. So why should there be a potential difference? This is actually quite easy to understand, but the analysis is a little bit more involved. So in that case, I'm just going to assume first that there are positive charge carriers inside. So let's just keep in mind that the current is in this direction. So let me draw this current that way, right? So the current in here. I'm going to draw the motion of the charge carriers in here. So if I have a charge carrier in here, in that case, it has a drift velocity in here, which is parallel to the direction where the current is positive. So as a result, this charge carrier is moving along that direction. So because of that, of course, since it is moving inside a magnetic field, there is a magnetic force on it. I'm going to show the force with a white color. You can see that this force pushes the charge in towards that side of the wire, right? So there is a magnetic force in here. So let me write F mag, right? There is a magnetic force that pushes this charge particle along that direction. So there, as a result, this charge particle is going to deflect. And they are going to deflect, of course, to that side, which means, of course, this is not the only charge particle in here. There are many charge carriers. So all of them get deflected to that side. They are going to be pushed to that side. So that means that side of the wire is going to be positively charged. But since the whole wire is charge neutral, they are going to leave behind negative charges. So as a result, this other side of the wire, this side is going to be negatively charged, which means, of course, as a result of that charge pileup, there is going to be an induced electric field along that direction, right? From the side where the point A is to the side point B is, right? This is because the electric field is in the direction of from positive charges to the negative charges. Okay, so that's the whole electric field, right? That's what we are calling about this. So this is the whole electric field. So in this case, for example, you can see that the point B is at a lower potential than A. So in that case, the whole potential would be negative. I mean, at least this VBA potential difference is negative. Let me not compute any value for this. We just need to understand this qualitatively, right? That's the reason why there's a potential difference between these 2 points, because somehow the magnetic force deflects all these particles, charge carriers, to one side. And so as a result, there's some kind of a charge distribution between these two sides. And so therefore, there should be a potential difference. But we can understand how large the whole electric field should be. Well, this is the place where the crossed electric magnetic field idea actually appears. So in that case, the whole electric field, sorry about this, is perpendicular to the magnetic field. And somehow this electric field should reach to such a value that after everything has settled down, these charge carriers will not deflect anymore. So as a result, this is the idea in here. So the whole electric field has such a value, right, is such that basically the whole electric field cancels the deflecting effect of the magnetic field. So therefore, this is going to be equal to 0. Unfortunately, in here, all the charge carriers are moving with different velocities, but it appears that this equation has to be satisfied for the average velocity. So therefore, we write down the drift velocity in here. So somehow, this arrangement of the applied magnetic field and the produced whole field plays the role of a velocity selector, where the velocity selector kind of selects this drift velocity that the charge particles are moving. Okay, so this is the essential idea in here, and you can see that in here, by measuring the whole potential difference, you can measure the whole electric field. And once you know the electric field, and you also know the applied magnetic field, you can measure the drift velocity in here. You can we can measure VD. We can not only measure its magnitude, we can also find its direction in here. So that's the interesting thing, because this drift velocity actually depends on the sign of the charge carrier. So for positive charges, of course, this is parallel to the direction of the positive current. But for negative charge carriers, the drift velocity should be opposite. So as a result, let's quickly see what happens for negative charge carriers. So I'm going to draw the same picture again in here. I'll try to draw, right? That's the rectangular slab in here. We have a magnetic field like that, right? We have a current flowing like this. The current is along that direction. Current is flowing like that. This is the point A, this is the point B. But now we have negative charge carriers. So in this case, what happens? I know that if this current is positive along that direction, in that case, the negative charges are moving in the opposite way, right? So that means V cross B is this time opposite from A to B, right? It is along this direction, so that's the direction of V cross B. V is the drift velocity, which means the magnetic force is again towards right. So therefore, there is a magnetic force acting on this negative charge, which is pushing the charge in the opposite direction. So as a result, they are going to deflect. So this time the A side would be negatively charged and the B side would be positively charged, which means there's going to be a Hall potential, Hall potential difference. This time this is pink, but that's okay. There's a Hall electric field, but this is going to be in the opposite direction. So therefore, this VBA in here, that's the Hall potential. That should be positive. Okay, so for negative charge carriers, therefore, the Hall electric field developed would be from B to A, and the Hall potential would be positive. Let's go back. For positive charge carriers, the Hall electric field is from A to B, is in the opposite direction, and the Hall potential would be negative. So by measuring the sign of the Hall potential, we can understand the sign of the charge carriers, right? So the essential idea is in here is that somehow the Hall electric field is such that it cancels the magnetic force acting on the charge carriers on the average. And so as a result, the Hall electric field together with the magnetic field, they behave like a velocity selector for the drift velocity. So as a result, from the measured value of the Hall electric field and from the known value of the magnetic field, we can measure the drift velocity here. By using the drift velocity, of course, we can also measure other properties like the density of the charge carriers and things like that. So as a result, because of that reason, the Hall effect is a very important measurement tool for understanding the properties of the charge carriers.